Hello everyone, I am the 7th craftsman from Maritime Craftsman School. Next, I will introduce the C-Code software to you. Our school requires that before presenting a video, we must first explain the theory. But recently, I've been quite busy at work and haven't had time to thoroughly go over the theory of SIMA, so in today's video, I'll first guide everyone through the simplest practical operation of a mooring vessel. Or it could be a semi-submersible platform or a floating crane, basically any floating structure. I'll show you the basic modeling and operation methods in C-Code. In the following sessions, I will introduce one by one topics such as lifting operations, berthing simulations, towing net cages, or FPSO TLP platforms, and so on. In the subsequent video explanation, because the SIMA software is quite powerful, I hope you will point out any errors in my explanation. Okay, let's open the SIMA software and work directly on the design data on the left. We right-click and select New Key. Create a new reflex condition. I will explain the difference between the reflex test and the CN test in a later video. We will introduce them to you one by one. Rename this newly created condition and give it any name you like. Alright, now let's expand it. Once the expansion is complete, let's first take a look at its three-dimensional perspective. Okay, this is the 3D view of the new condition we just created. Now, there are some red crosses in the folder on the left which represent errors. You can ignore them for now. Right-click on the blank area. Select to import a CSIM interface file. Alright, click Next. Here, you need to select the G1 file generated by WADM after completing the translation analysis. Okay, I will select this G1 file. Click Finish. Now you will see that a new CM condition has appeared below. Next, I will expand this CMOR condition. Expand the model, and under Bodies we can see there is Body 1. Expand Body 1, and below it there is a folder for coefficients. Under this coefficients folder, we can see the hydrodynamic coefficients imported from the G1 file. For example, this is the model's mass and moment of inertia information. Below that is the model's added mass stiffness. Further down are the transfer functions for motion, followed by a section on wave particles. Finally, there is also added mass and damping. It also includes some contents related to retardation functions. Some additional information. These are what is included in our G1 file. We don't need to worry about the hydrodynamic coefficients. Alright, let's right-click to copy it. After copying, paste it into the newly created one. Oh, I need to create a new body here. Copy it under the newly created body. Okay, in this way, the body in the newly created reflex condition now has hydrodynamic coefficients, so we can delete the old one. Next, we need to set up the environment. First, let's click on Location. Set the water depth in the location section. The depth is 200 meters. Alright, then we click on Sea Surface. I'll set the width of the sea surface to be larger. You can follow along and set it with me. Okay, then we click on Seabed. The vertical coordinate of the seabed should be changed to match the water depth, which is minus 200 meters. Then adjust the seabed. Make the area a bit larger. Alright, the basic environment has now been set up. Next, double-click on Body with the left mouse button. In the low-frequency motion section, we choose not to separate or estimate. In other words, there is no need to provide a separate low-frequency component. After setting this, you'll notice there's still a red error arrow above. This is because the reflex condition requires the body to be connected to a finite element beam. So, we need to right-click here. Create a new connection. Specifically, it's a slender system connection. Once the connection is created, you'll notice that the red arrow in the upper left corner of the body has disappeared. Alright, let's just leave this connection here for now and not worry about it. Next, we need to create a new supernode. Right-click and select Create New Supernode. Okay, let's rename it to the origin of motion, which is the reference point for the movement of this body. The one below doesn't need to be checked. Then navigate back to the Network Connection Options menu. Select the supernode here. Select the supernode you just created. Okay, let's move on. Let's take a look at the model. Let's find the body we've created in my 3D view. Now we can see that tucked inside this bag is a small, bright red box. But what we want is for this box to be a ship, so we need to select the finite element file in the geometry type, not a box. Note that in SIMA, whether your body is displayed as a box or as a ship has no effect on the motion. It's only for display purposes. It's just to make the animation look better when you watch it later. Okay, I just imported T1. Let's take a look at this ship. After the ship model is imported, the next step is to prepare for modeling the mooring system. Because this ship is moored. A thin line, as we know, is composed of a start point and an end point. So, we first need to model the start and end points, which are our supernodes. Under Supernode, select Create New Supernode. Change the attribute of the supernode to Slave. Slave in English means servant or subordinate. Here you can understand it as follows. The attribute of this supernode is a subordinate relationship, meaning it will move along with another master node. Alright, let's set the master to be the origin point that was just in motion. This step can be understood as the point at the mooring line's guide hole moving together with the floating body. In other words, your floating body is pulling the thin mooring line along as it moves. Alright, after renaming one, let's create a new one. The mooring line, at the point located on the seabed. I'll name it Anchor 1. The point on the seabed is fixed and does not move, so in its properties, we select the fixed attribute. Next everyone, follow me and enter the coordinates for the seabed anchor point. Alright, after the seabed anchor point is created, we need to create the next point for the guide tube. Rename it to F2. Of course, its attribute is also Slave. Its master is also the origin of the ship's movement. Next, let's model the second mooring line, the anchor point of the second mooring line on the seabed. We'll go ahead and rename this point to the second anchor. Then enter its position coordinates. Next is the third mooring line. First, create a new point for the position of the third mooring line's fairlead and name it F3. The attribute is still slave. The master is still the ship's movement origin, right? Then create a new anchor point for the third mooring line on the seabed. Everyone should remember, the start and end points of the mooring line are determined by the supernodes. Alright, now let's take a look at the model. Because in SIMA, we haven't created the mooring lines yet, we've only created points, so there aren't really any changes to the model. What is currently displayed is not the mooring lines because we haven't modeled the mooring lines yet. Next, we need to create a cross-sectional property. That is, define the cross-section of the mooring line. Alright, in the cross-sectional properties section, let's refer to something here. I'll refer to the one from a previous model. There are 3 values, you can follow along and input them with me. First, we need to enter the diameter of the mooring line. Alright, let's turn this off first. Copy it over. Next, we need to input the cross-sectional area of the mooring line. Alright, then it's the tensile stiffness of the mooring line. Note that here I'm using the bar element. One is the bar element. You can also set it as a cable element. The difference between the bar element and the cable element is that the bar element has stiffness in 3 directions, while the cable element only has stiffness in 1 direction. You can think of the bar element as a very stiff pen. Whereas the cable element is like a rope, you can pull on the rope, but you can't bend it. Alright, after we finish defining the cross-sectional properties, we need to create lying type. So, right-click to create a new one and select lying type. You can think of lying type as the property for subdivided fine wires. Let's change its name here. Then, select the cross-section we just created here. Next, we need to enter the length. I'll refer to the previous model for the length. Alright everyone, follow along with me and enter it together. For the segments, change it to 80 segments. Okay, next we can go ahead and create the Zibo County, as well as create a new lie. Right-click and select New Lie. Alright, in the line, select the line type we just created. For end 1, choose our starting point, which is the point of our guide hole. So, select F1. End 2 is our anchor point on the seabed. Alright, now you'll notice there's a red error message. But that's okay, we're here. Under anchor 1 below. Select the door. Oh, right. You need to add the newly created pulling property as well. Click here to select the line we just created, and the red error will disappear. Alright, let's create the second fine line. Select New Lie. Keep the line type unchanged. For end 1 here, we need to select the point of the second guide hole, which is F2. For end 2, select anchor 2. It's the same operation. Create another one. From F3 to anchor 3. Oh, it seems I selected the wrong one here, but that's okay. Alright, let's go back. Anchor 3. Oh, sorry, I just selected the wrong one. I think I didn't select anchor 3 just now. I chose F3 twice. Alright, it should be fine now. Okay, with this, our tinfoil lines are now fully modeled. Let's take a look at the model now. Now I notice that the direction of my ship seems to be facing outward. I will make the necessary corrections right now. Select this ship. Let it face the X direction. Then left-click on this pad. Under the body section, set a rotation here. Of course, this rotation is just for display purposes. It won't have any effect on the results. Alright, after making the correction, let's create a new environmental condition. Right-click on Experiment. Then, under the options below, select Waves. Choose the 3-parameter spectrum. First, just enter any wave height and typical wave period. Next, go to the dynamic settings. Make a series of settings, such as the analysis time. Now I want to reduce the analysis time a bit. Then we select. In the storage section, let's enable animation storage so it's easier to view the animation later. Next, in the boundary changes section, we need to take the one we just set the original motion origin, which was fixed, to free and release it. Otherwise, your ship won't move. This step is very crucial. Alright, next we can create a new condition to perform the dynamic analysis. if your settings are correct. Many students encounter a lot of errors when learning SIMA, but if your settings are correct, there won't be any errors during the dynamic analysis. Okay, let's wait for a moment, alright? Once the dynamic analysis is complete, we can take a look at the results. In the results section, we can check the motion results. You can also first take a look at your desktop. This is your desktop's force curve. Below are the 6 degrees of freedom motions. For example, we can look at the surge motion in the set direction, the motion in the T5 direction, and the motion in the roll and pitch directions. This is the hand-cranked motion, which might be because the mooring lines are too tight, causing the hand to move a bit awkwardly, but that's okay. Alright, now we can take a look at the animation of the motion. Up here, we select Dynamic. Everyone can take a look. This is the ship I connected. The animation of the motion. It might not be very obvious, but the wave surface is moving. If any of you encounter a lot of errors during the simulation process, you can also roughly see in this animation window at which step the error occurred. If your model sinks, it might be because your buoyancy is not set correctly. Alright, that's it for today's tutorial video. Thank you all for watching. This example is very simple. In the future, I will introduce some slightly more complex models to everyone.